Hello, my name is Farid, and today we are going to take a look at C++ functions. By functions, I do not mean the strict traditional definition of functions, but rather I'm going to point out the concept that is best described by callables. In this session, we will take a look at C free function pointers, then try to implement the observer pattern using these function pointers. Then we will take a review of steady function and what C++11 brings to the table. After that, I will try to show a different usage of function pointers, and then I will introduce a few functions and classes that I would like to have in my utility for functional programming. Just like declaring a function, in order to declare a function pointer, we need to specify the types of all of its arguments as well as its return type. Initializing and assigning to a function pointer is just as simple as an ordinary pointer, but we can also remove and omit the address operator for syntax clarity. In order to call the target of a function pointer, we can dereference it using the dereference operator, or we can omit the dereference operator for syntax clarity. I couldn't find an accurate and strict statement about the relation between the size of a function pointer and its argument types or its return type. But there are two guarantees. First, all function pointer types are castable to each other, so we can cast the function pointer to other function pointers and back to the original pointer type without loss of precision or information. Moreover, we can cast to and from a void pointer, so we can store every function pointer as a void pointer when necessary and cast it back to the original type in order to call without losing any information. Examples of usage of function pointers in standard C library include the signal function, which is supposed to register a user-defined function as the handler for specific interrupts. Another example is the qsort function as the generic sort function in the C library. This function expects a binary predicate in the form of a function pointer. The parameters to this function are type erased through use of void pointers. The only information available about the type of array elements is the size parameter used to iterate through the array and the compare function who knows the types completely. Similarly, the bsearch function performs a binary search over an array to find the element matching a specific key. In order to do that, it needs a binary predicate, again in the form of a function pointer, and use of void pointers again erases the types of the arguments. The type information is again transferred through the size parameter and the predicate comparator. Function pointers are widely used in UI event management applications as callbacks. FLTK is one of those UI event management libraries. The callback function of an FLTK window can be used to register a function as well as the data it needs to respond to an event originating from user interaction. Similarly, in Photon UI from the QNX RTOS, we have the ptadd callback function. This function adds a specific function along with its data and the event queue of a specific event for a widget. The callback system of QNX Photon is a good structured implementation of the observer pattern. This is the pattern of choice in designing many event-driven libraries for UI applications. The subject or event handler is eventually a collection of observers attached by user code at runtime. Upon the occurrence of an event, the subject notifies its observers with parameters describing the details of the event. An observer can be regarded as a pair of a function and its associated data. This function is then called through the notification using the extra data provided by the notification mechanism. The notification syntax in C++ UI libraries is generally a function call. The challenge in C++ used to be to find a mechanism to implement a template class for the event handling mechanism. This class should have been able to instantiate observers of user-chosen number and type of parameters. We can use vector as the implementation of the collection class in implementing the subject class we talked about. We will focus on implementing the notification method, which is the function call operator. Therefore, we leave the callbacks data member public for simplicity. Defining the special case was not a big deal, but once we want to generalize it, we get into big troubles. Prior to C++ 11, we had no good solution to provide a generic implementation. There are several bleeding points in our simplistic class, and you can see them. Providing variadic arguments to the class and the function call operator was a great challenge. No good solution was provided. The only solutions available were ad hoc tricks and macros and greedy macros that most of them were not portable. Moreover, overuse of preprocessor was not satisfactory. Eventually, mainstream providers took their own directions. Microsoft actually implemented the feature as a core basic type using a non-standard keyword named delegate. On the other hand, Qt chose the path of code generators. Code generator is actually an extension of C++ preprocessor with more abilities and customized capabilities. Qt calls its preprocessor or code generator meta-object compiler, or contracted as MOC. In this snippet, QObject and QSignals are two Qt macros that the meta-object compiler uses to inject its generated code. The pair of an object and its signal function pointer serves as the identifying handle for the actual subject, and the observing object must register a member function on this subject. But none of these solutions satisfied the library developers. These solutions lacked extensibility and scalability. This was the ground on which Doug Gregor made his revolutionary proposal. In this slide, you can see some major library utilities using variadic templates in their relative impactfulness order. The integer sequence library emerged a bit late, but it made the implementation of other libraries much simpler. It made the non-recursive implementation of these libraries possible, which led to shorter compile times. Tuple was a successful, fundamental, yet growing library. The variant library took a very long journey before adoption into the standard library. Stud function was one of the major reasons for adopting the variadic template proposal. It is a very elegant and useful library, but I usually think twice before recommending it to newbies because of its memory demands. Studbind is another useful library which is normally used in conjunction with the stud function. It's a very well-defined library, but the cryptic messages when an error is detected is a major problem. The reason is the problem with constraining such variadic templates for functional programming. Finally, the boost signals library is the implementation of the observer pattern we were seeking. One of the major contributors of this library is the original proposer of the variadic templates proposal. Although the boost signals library covers the agenda that we were following in our simplistic example, we will still push a bit more on the example for the sake of illustration. We want to show how to use the syntax and semantics of variadic templates. The generic definition of our event handler doesn't do anything functional or useful. It just provides a default value for the second argument, which will be the only acceptable value for that argument of this template. And that argument is a function of the given signature. The specialization actually implements our class using the readable syntax of variadic templates. We can see the usage of parameter packs and pack expansions in this implementation. Since we are not going to use the return type of our functions, this implementation is rejecting the non-void functions through the static assert. The C++ 17 version is just a bit better optimized in terms of compile time, because R values are not good arguments for our signature, because R values are single shot by nature, but we are going to use our parameters several times, passing them to multiple observers stored in the vector. So R values are not good candidates, and signatures that use R value arguments are not acceptable. Eventually, this class will fail with signatures that have R value arguments, but we want to get a fast failure in such cases so that compilation stops faster. Finally, we can instantiate our event handler class. We are targeting functions accepting one single integer and returning nothing. We can use a function with exactly matching signature, or we can decorate non-matching signature functions using the bind library. The bind front utility is actually a C++20 extension, but there are workarounds that can work with previous versions of the standard. We will keep bind front because of its simplicity. We can use the bind library to decorate member functions too. In this example, we have bound an object and a false value to the extra parameters of the update function from the observer class. This update function is actually incompatible with the signature we were targeting, but using the bind front function, we have actually decorated the type of this function. We will be in trouble if we change the type of elements stored in the collection class of our event handler. If we change the element type from standard function to an ordinary free function pointer, we will face compilation failures. Actually, the only case that compiles is the exact match signature free function pointer we used in the first pushback. We cannot add any other forms of functions to our event handler class. We have lost generality using the function pointer syntax. That's because function pointers are not stud functions. We will see different kinds of functions in C++ in the next slide. The stud function is capable of erasing the types of 4 general classes of callables. The first type is free function pointer, the C-style function pointers. As we have discussed earlier, these type of pointers can be stored in the memory required to store a single void pointer. One way or another, through casting to void pointer or not, we can find a way to store this type of callables in a single void pointer. The next class is the instance member pointer. Instance member pointers are entirely different beasts from the previous species. These kind of pointers have a size depending on the defining class. Their size depends on the hierarchy of the class they're defined in. They're not castable to void pointers, neither are they castable to static function pointers. The next class is user-defined function objects. These type of classes are signified by the existence of function call operator in the class. A specific case of function objects is the lambdas. These type of classes can be cast to void pointers if the capture list is empty. Actually, they can be casted to function pointers and then to void pointers because of empty capture size. The last input to the stud function is the self type. This type of functions normally needs more than 5 times the size of a normal void pointer as memory. However, on some platforms, I have seen twice as much as this number. That is, I have seen platforms where storing a stud function takes 10 pointer sizes. There are design decisions behind this size, and we will explore some of the obvious ones in the upcoming slides. And again, this huge size is one of the reasons I hesitate to recommend stud function to new programmers, because the memory demands are generally too high. The stud function is supposed to store 2 items. First, it should store information about type eraser. That is, it should remember the type of the object it is storing so that it can call the function call operator or other functionalities necessary when the user demands. There are two ways to implement this functionality. The traditional way is through using a virtual function and a hierarchy of classes. The second way is the way that stud.any used to type erase its stored objects. This strategy doesn't need the virtual keyword, doesn't use the traditional OOP style polymorphism, and can be beneficial in some embedded environments or environments where using the RTTI or virtual keyword is prohibited or restricted, or there are reasons to not use it. Again, type eraser without RTTI can be achieved through two strategies. We can store a pointer to metadata function or store a pointer to metadata structure, whichever is more efficient on our platform or uses less memory. The second item stored in a stud function is the small value optimization buffer. As with many other stud classes, this class too uses small value optimization. This buffer should be large enough to hold the most obvious cases of usage of stud function. For example, a free function pointer with exactly matching signature should not be put on the dynamic allocated memory. It can be stored in the small value buffer. Another example is binding a member method to its object via reference. This is a very obvious case, especially for programmers coming from other languages. A third case is binding a shared pointer to a function pointer. For this case, actually, we don't have the library facility needed. We don't have the deref function in the standard library. The deref function is a function that I wish I had in my library tools to bind a smart pointer to a function or a member function, because we sometimes need to worry about the lifetime of the object we bind to the function. Now we are going to review the least memory demanding category of callables in C++. But before that, we should take a look at monostate category of classes. Instances of a monostate class do not carry object-specific data, and all the instances of such class are equivalent. Therefore, such a class is not supposed to have instance data members or virtual functions. This means that such classes should satisfy the conditions of empty classes in C++ and trivial classes. That is, their special member functions must all be trivial. And none of the member functions should need to use the this pointer. Empty capture lambdas act very much like a monostate class instance. Specifically, these type of functions do not even have a this pointer to begin with. The user also can define classes which are both monostate and function object. That is, they both have a function called operator, and they have no data members, and they have no virtual members, and don't use the this pointer. It is simple To wrap the call to any function or member function inside a monostate function, either an empty capture lambda or as an user-defined function object class. Can we have a generic wrapper for the call to any function pointer or member function pointer? The answer is yes. We can use a template variable in C++14. I call that template variable Monostate from overload. This template variable needs the type of a function pointer or member pointer as well as its name as its parameter. C++17 enables us to use the deduced non-type template parameter. So long as the function is not overloaded, we can create a monostate function from that function through use of the monostate from template variable by passing the function name to this template variable. So in short words, we can use the monostate from templates variable for functions which are not overloaded, and monostate from overload to disambiguate overloads for overloaded functions. Thus, you can see that we can reduce the memory requirements of storing function pointers and member pointers to 0, because the monostate wrapping of the functions and member methods is empty. We can type erase monostate's functions of a specific signature in two ways. We can define a template function that converts the monostate function into a function pointer of that specific signature. This method has the caveats of generating UB, because it's possible to forget to initialize a function pointer or invoke a function pointer which is set to null pointer. We can also define a short function class which is capable of type erasing and storing any monostate function. Since the monostate function is an empty class, this short function is not supposed to store any data about the specific object. It only stores the eraser data about the type of the function. Therefore, it is no more expensive than an ordinary function pointer in terms of memory. But it also has the advantage that it can be defined so that it doesn't generate any sort of UB or exceptions. Because as a class, we can prevent it from having a random uninitialized state. And we can have this class to default construct the resulting value in case of a call to an empty function object. That is, if the short function is default constructed and is in the empty state, and an invocation request comes, the short function can return a default constructed value. If the return type is not default constructible, then the short function class cannot have an empty state. It cannot be default constructed, and trying to default construct short function for such signatures will result in a compile error. The behavior is well defined, no exceptions, no UB generated due to the definition of such class. We can use function pointer literals or member pointer literals to the short function through use of previously mentioned Monostate from and Monostate from overload template variables. That is, a short function can actually store a function pointer or a conversion of the member function pointers. The signature of a stored monostate function is not supposed to be exactly the same as the signature specified for the short function. It can store any monostate function provided that the stored monofunction is actually invocable with the arguments required for the signature of short function, and its return type is convertible to the return type of our signature. As mentioned earlier, this short function class removes any windows to generating UB through calling any member of the short function. If we have to use a short function to a class that doesn't provide a default constructor for its return type, and we need to have one empty state, we can use the optional standard library class. As mentioned earlier, the memory demands of a short function is no more than a void pointer. It is easy to define a conversion function from a short function to a pointer to its signature. Since a short function can be initialized from a function pointer literal and can be converted to a function pointer, it can safely replace the free function pointers used in old codes. This class is less generic than stud function. It can handle fewer cases. It only accepts monostate functions as its inputs, but at the same time, it is more optimized and less memory demanding than a std function. This class can be used in scenarios where we don't need to capture any data or bind any data to the function. Next, we can define a long function. It is a counterpart to the current std function, which is supposed to have less memory footprint. In order to achieve this less memory footprint, we should let the size of small buffer and its alignment be controlled by the user code. It is better for this class to have default values for size and alignment of its small buffer according to the platform. This class is supposed to store any callables that std function can store, with one set of exceptions that will be mentioned later. Like short function, the long function class should not be source of any UB or exceptions. That means this class has an empty state only if its result type has an empty state. Default construction produces that empty state. Invoking an empty long function results in default construction of the result type. If we need a long function with an empty state whose result type doesn't have a default constructor, we can use a stud optional return type instead. Because this class too can accept compatible signature functions, we should prohibit member functions and function pointers as inputs to the line function class. We need also prohibit bindings of function pointers and member pointers as inputs to the line function class. Otherwise, we might end up storing a null pointer or random value inside our line function. Function pointers and member pointers should be fed through use of the monostate from and monostate from overload template variables. It is also possible to perform an optimization when converting a short function to a line function. That is, instead of erasing the type of a short function into the line function, we directly erase the underlying monostate function stored in the short function. Our line function class has the same abstraction level and genericity of the stud function, so it can replace stud function in most use cases. The only difference is that this line function class cannot store direct bindings on function pointers and member pointers, as well as directly store member functions and function pointers. It needs to store monostate from function pointers and member pointers, but that's not a big deal. It can handle all cases that the stud function does. In many functional libraries like studmind library, we have a problem with the level of abstraction we're dealing with. When defining such function objects, we normally define the function call operator as generic as it can be, and constraining this function call operator is a major difficulty for us. We normally use the universal variadic argument list for the function call operator. This pattern has the benefit of simplicity and using perfect forwarding to optimize out the unnecessary copy-move operations. But at the same time, it has the downsides of defining unlimited number of overloaded function call operators, as well as cryptic diagnostics when an error occurs in the program, and also the case of copy elision, which is the newest optimization adopted into C++ language, is disabled. We're gonna need some traits to overcome this difficulty. The standard basically provides us with two generic tools. One of them is the isInvocable trait to test for the invocability of a callable with a set of arguments, and the second is the invoke result that gives us the return type of using a callable with a given set of arguments. But that is not enough for constraining the functional libraries as efficiently as we need. The challenges on defining a properly working trait library includes the level of diversity caused by qualifiers on functions and member functions. For a member function, we could have more than 16 variations according to existence or absence of CV qualifiers, R value, R value and L value qualifiers, and the no except qualifier at least. Free functions are no better than member functions because we have abominable functions. As weird as their prototypes may look, and as rare as their use might be, that is close to zero, they are part of the language, and declaring such functions is not prohibited. So the traits classes need to consider all these cases, which is tedious and a major setback for designing such a trait library. But our unbeatable open source community, the boosters, have provided us with a callable traits library since version 1.78. It has a bunch of useful tools inside it. The two that might catch my eyes are the return type and args_t. If a callable or a function pointer or a member pointer has one single function call operator which is not overloaded, then return type gives the return type of the function given its type. No more arguments needed. Under the same condition, the args_t gives the tuple of all arguments a function needs. Basically, this tuple is the tuple that can be applied to the function or callable. There's more to this library, but these two tools are sufficient to show the elegance of this library. In order to avoid a complex pattern whenever we need to define a generic function object class, we can do the hard work inside the function-based CRTP class. This class defines the unique function call operator that accepts the exact set of parameters as the callee of the function. This CRTP based class also can define the traits necessary or related to the signature of our function. The function call operator of this base class eventually forwards the parameters to the doInvoke member of the derived class. The doInvoke member of the derived class can be an ordinary generic variadic template. The function call operator of the function-based class chooses the proper version and instantiates it. In the derived class, we do not need to worry about the signature of our function call operator. The task is handled inside the function-based CRTP class. Like our event handler sample class, this function-based CRTP class has a generic definition that doesn't do anything special and is therefore disabled with a static assert. The actual definition is defined inside the specialization of the class. In the specialization of the class, we can define the signature of the function as well as the return type and the argument tuple. The argument tuple is the tuple that we can feed to the apply for this function type. Then we can have the count of the elements and the argument type by index of the argument. And of course, the unique function call operator that uses the exact signature of the function that we need. This operator is supposed to forward the parameters to the doInvoke member of the derived class, which we already have defined as a generic variadic template. In this implementation, we haven't considered the case of const function or maybe R value or L value function call operators, because we just need and demand a single function call operator. If we need to consider all those cases, the definition of this CRTP class may become a little bit more complicated with maybe extra parameters, and we may have to define up to 4 specializations or 4 distinct classes. But the basics are just the same as we have illustrated here. During preparation for this talk, I came to the conclusion that core language could be improved in 2 ways that helps functional programming. First of all, we missed the tail call optimization in C++ programs. As we know, copy elision and perfect forwarding are exclusive due to the reliance of perfect forwarding on universal references, which are in turn instances of references. That is, every argument of the function is converted to a reference using the perfect forwarding syntax, and that prevents copy elision in cases where it is possible. A tail call is actually the combination of both perfect forwarding and copy elision. It forwards the references and elides copy and move if the signature of the callee and the invoker are the same. A tail call actually consists of 2 stages. It unwinds and cleans up all the automatic objects created during the execution of the function, but keeps the parameters and arguments of the function intact because we need them for the tail call. Then it unconditionally jumps to the target function that we are trying to call via a tail call request. In my opinion, the tail call request shall need a specific syntax, a little bit different from a normal return. And I think assigning to the return keyword is the proper way to do it. So if we could devise such a syntax, we could ask for a tail call in our generic function object libraries. Next, I discovered that the const per everywhere idiom in standard library can actually become problematic in some cases, because the const per keyword puts a top level const on the return of the function it defines. And if the function is a forwarding or a generic function like invoke or apply that forwards its parameters to the actual callee, then the return type is actually changed to the const version of itself. This is specifically problematic for return types that are non-const references. By adding a const to such references, we will fall into trouble, and we have to play some roller coasters to cast them back to their mutable states. The solution can be to define 2 overloads for the invoke or apply functions or functions like them, but since the implementations are similar, that would lead to code repetition. In order to avoid that code repetition, I think the best solution is that the const expert itself becomes a conditional keyword, just like the explicit and no except keywords, so that we can rule out the cases that we don't want the function to be const expert inside the condition. Here you can see a summary of what I wish to see in the future of the functional programming with C++. I would like to see a syntax for tail call requests that can optimize the definition of our generic functions, and we can make the const expert keyword conditional just like the explicit or no except keywords, which makes our generic code more flexible. We can have a deref function that enables us to use bind libraries with pointers to parameters of functions. That is, we can bind functions to smart pointers of their parameters and manage the lifetime of bound parameters by using correct smart pointers alongside the deref function. And we can have the function base CRTP class for generic function libraries that simplifies defining a unique function call operator with exact signature and provides the traits for our functions. We can have a monostate from template variable that converts its only non-type parameter, which is a function pointer or a member pointer, to a monostate empty trivial function object that can be used to optimize memory usage of functional libraries. We can use monostate from overload instead of the monostate from in cases where if we have an overloaded function or member function, and we can disambiguate the overload using the type of the function pointer as the first argument to the monostate from overload and the name of the function pointer as the second parameter, and we won't need to use the casting and casting syntax. We can have a short function class that erases the types of all monostate functions or trivial empty functions and can accept any trivial empty functions as its input. It can be a good replacement for traditional freestyle function pointers in C++ code. And we can use a line function template as a successor replacement for stud function, which enables the user to customize the size and alignment of its small buffer. And the only functional difference with stud function is that this line function doesn't allow naked function pointers or member pointers or their bindings as its input. It should use monostate from or bindings of instances of monostate from variable template instead, in order to avoid exceptions generated from null pointer and traditional empty state management. Thank you for being with me up to this point. I'm Farid from Iran, and I'm very lonely and alone in my journey with C++ here. So what I've done so far may be very far from perfect because I'm too alone. I need pals to help me fix my mistakes. I need some mentors to tell me whether or not I'm in the right direction or which direction I have to take in developing C++ libraries. Then I need peers to constantly correct my errors and give me hints about the bugs in my library and in my efforts. I also need some friends that can help me document what I've done so far or what I will be doing, because I'm really terrible at expressing what I think and what I do. So I need people with experience and ability to help me create correct and understandable documents about what I do. My Gmail address is farid.mehrabi@gmail.com, and I'll be happy to hear from you. Thank you for being with me. Have a good time.